Um, Hello and welcome to my channel. In the previous video, I showed you how to draw the shear force diagram and the bending, the bending moment diagram for a cantilever beam with a point load by the end of the beam. Here we'll do a similar example, but with a distributed load for a simply supported beam. So we have, this is a beam and it is simply supported, so we have the pin joint on the left and roller support on the right, and we have a distributed uniform load like this. Okay, it is 3 kilonewton per meter and the length is 4 meters. Okay, as we mentioned in the previous video, so we have mainly 3 steps. Step 1 is to calculate the support reaction. Okay, so let's do it. We have, this is the beam and we have pin, roller and distributed load. And for the pin support, you have 2 reactions, X and Y, and for the roller support, you have only 1 reaction in the Y direction. So I will say, let's say this is point A and this is point B. So at point A, we have Fy at A and we have Fx at A, and for point B we have Fy at B. Okay, so you have 3 support reactions, and you know the equation of equilibriums: summation Fx equals 0, summation Fy equals 0, summation moment equals 0. So summation Fx equals 0, that means Fx at A equals 0. And then summation Fy equals 0, that means Fy at A upward direction, that means it's positive, plus Fy at B, the same, it is upward, it's positive, and then minus the distributed load. So in this case, we will convert the distributed load into a concentrated point load. How can we do this? By calculating the area of the distributed load. Okay, so this distributed load was 3 kilonewton per meter, and we have this length as 4 meters, right? So calculate the area. It is a rectangle, length by width. The length is 4, the width is 3 kilonewton per meter, so the area should be 3 times 4. This is equivalent point load to this distributed load. And for sure it will be pointing downward, so we have the negative sign. This will be equal to 0. That means Fy at A plus Fy at B equals 12. Okay, last equation, summation moment about the z direction equals 0. And in this case, you can take the moment about A, you can take the moment about B. Both would be the same. So let's take moment z about A. Equals 0. Okay, so about this point, you have Fy at B times 4, right? And this would be counterclockwise, so it would be positive. And then you have the distributed load, and we agreed that the equivalent point load is 3 times 4, 12. But where is the point of action to this point load 12? So the point of action is in the centroid of the distributed load shape. So in this case, the shape is a rectangle. So the centroid of the rectangle in the middle at this point, 2 meters from the right, 2 meters from the left. So if you want to add this 12, so it will be right here in the middle, 12, and this will be kilo Newton. There is no meter because this is point load. So it will be 12 kilonewton. You multiply the 3 times 4. Okay, so the 3 has the unit of kilonewton per meter, and the 4 is meter, so you multiply these two, this will give you kilonewton. So this 12 is kilonewton, and it is acting in the midpoint of the beam. So while calculating the moment around point A, it will be 12 times 2. Positive or negative? Yes, you are right. It should be negative because it is clockwise direction. Okay, and this should be equal to 0. From here, you can calculate Fyb. This should be equal to 6 kilonewton. Okay, go back to the Fy equals 0 equation. Now you have Fyb is equal to 6. So you want to get the Fya using summation Fy equals 0 equation. You can give it a number and refer to it as well. So this will be Fy at A plus 6 equals 12. Then Fy at A equals 6 kilonewton as well. Okay, now we got the support reactions. The second step is to calculate the shear. Step 2. get the shear and shear force, sorry, and bending moment functions. Okay, how can we do this? By making a cut in the beam and see what is the function of both shear force and bending moment diagram. So okay, so we have this beam, and now we know the support reactions. This is a distributed load, (3 kilonewton per meter), and we have here 6 kilonewton. We have here 6 kilonewton, and we call this as B, we call this as A. Okay, so let's do the cut in the beam and see how can we find the support, the equations for shear force and bending moment. We can do the cut anywhere in the beam, so let's see if we did here, and then the left side would look like this. This is point E, and this is the force, 6 kilonewton, and this is a distributed load. We have 1, 2, 3. Okay, and as you know, we are measuring X from here, so this is X. And now the shear force is here, V, and the moment is in this direction, M. Okay, then solve the equation of equilibrium. In this case, summation of X will give us nothing because we don't have any forces in the X direction. So summation force in the Y direction equals 0. That means the 6 kilonewton pointing upward minus the V, the shear force pointing downward, this should be equal 0, and that means V is equal to 6 kilonewton. Okay. We forgot to add the distributed load. Wait, so this is not right. So we have the 6 kilonewton is pointing upward, and we have the distributed load, which is 3 kilonewton per meter. So pointing downward, that means 6 minus 3 times how much is the length? Is X, right? This is how we calculate the equivalent point load for a distributed load. The area of the distributed load, 3 times X, and then negative shear force downward, this will be 0, so the shear is equal to 6 minus 3x. This is the equation of the shear force. And then let's do the bending moment. And as I said in the previous video, I prefer to take the moment about the cut point right here. Okay, so summation moment about Z equals 0, So we have the moment M, okay, and then we have the 6 kilonewton, and it is multiplied by X. This is the length, and this should be negative because it is clockwise, and then plus the point load equivalent to this distributed load. We said it is 3x, right? It should be here. This is the 3x, and it is acting in the mid of this distributed load. So this distance should be x over 2. Okay, so 3x times x over 2. And this is positive because it is counterclockwise. Okay, this equal to 0. That means M is equal to 6x minus 3 over 2x squared. Okay, so the third step is to draw shear force and bending moment diagrams. And I always prefer by starting with the beam itself. This is the beam itself. We have beam support, roller support, distributed load, (3 kilonewton per meter), point B, point A, and then we will do the two plots for shear and moment under this beam. So this would be for the shear, and this would be for the moment. This is moment M, here it is positive, negative, and then this is the shear V, positive, negative. Okay, let's go to the equation of the shear. So the shear V is equal to 6 minus 3x, and the moment 6x minus 3 over 2 x squared. Okay, so for the shear, in case of x equals 0, so you have 6. So you will start with a positive 6. Right? Some point here, this is 6 kilonewton. Okay? And then for x equals 4, the length here is 4 meters. For x equals 4, so this would be 6 minus 12. So it will be negative 6. So you will go here, negative 6. And then you will join these two together. And if you want to know how much is the value of x in case of shear is equal to 0. You will equate this to 0, so it will give you 6 minus 3x equals 0. That means x is equal to meters. So right here in the mid of the beam at x equals 2 meters. Okay, so let's go to the moment. So moment in case of x equals 0, the moment will equal 0. In case of x equals 4, so this will be 24 minus 3 times 16 over 2, which is also 24. So this would be 0 as well. So it starts at 0 and ends at 0. But it has a parabolic shape, x squared, and it is negative x squared. And you know, if you are plotting x squared, this is y equals x squared. And this is y equals negative x squared. So it is a parabolic shape like this, y equals negative x squared. But we don't know how much is the value of the moment at x equal 2 or any point between 0 and 4. So let's substitute at x equal 2. At x equal 2, the moment is 12 minus 3 over 2 times 4. How much is this? 6 kilo Newton meter. So at x equal to we have moment of 6 kilonewton. 6 kilonewton dot meter. And it is a parabolic shape, so it will be something like this. To make it more clear, we are doing it like this. Okay, and the same for the shear. And that's it. I hope this